record. Okay. Okay, so now we've converted this expression. Let's draw what these bounds are. So this tells us that y goes from 0, so y goes from 0 to y equals square root 1 minus x squared. If we simplify that, that becomes y squared equals 1 minus x squared, or y squared plus x squared equals 1, and that's a circle. So we have our circle here. Specifically, it's only going to be the upper part because we start from y equals 0 to y equals this circle. Then our x bounds go from 0 to 1. So this is going to be our region highlighted in yellow. So now when we're doing polar bounds, for r, we want to draw, again, a line in increasing radially outwards. We start at the origin, which is r equals 0. And then we end at this circle part, which we said was y equals square root 1 minus x squared. But we want to rewrite that in polar coordinates. So what is that in polar coordinates? Well, we said that's y squared plus x squared equals 1, or r squared equals 1, or r equals 1. So that's our upper bound for r. Then for theta, we can just look at in general, like think about a unit circle. Theta goes from 0 to pi over 2. That encompasses our whole region, 0 to pi over 2. Any questions on how I converted to polar? Okay, so let's move on to cylindrical coordinates. So now triple integrals. Okay, so slightly, okay. So then for cylindrical, these are some formulas that you might need to know if you're converting from cylindrical to rectangular or rectangular to cylindrical. Okay. Then we have Fubini's theorem for so we see that we keep doing Fubini's theorem with some like little changes. So this is Fubini's theorem for triple integrals in cylindrical coordinates. Now we know that dv, so triple integral, so dv is going to be dz, dx, dy, or dx, dy is like dA also. But remember above we said that dA equals r dr d theta. So that's this whole part. So in triple integrals, so now here when you're doing like this type of question, it's very easy to forget this r because it's like randomly in the middle. So don't forget it. And then how do we find our bounds? So let's just do an example. Okay. So it says find the limits of integration over d in cylindrical coordinates where d is bounded below by a plane, laterally by a circular cylinder, and above by a paraboloid. Okay, so first, you don't necessarily need to draw the picture, but in case I will draw it for you guys to see. So it's going to be, we have some cylinder, and it's bounded laterally by the cylinder and bounded below by a plane. So we know this is some flat surface, and then above by some paraboloid. So we don't know what this, if the paraboloid looks like this, or if the paraboloid looks like this, but either way, it's gonna like stop somewhere by this paraboloid. I can draw like that. So our region is gonna be bounded above by a paraboloid and below by the plane, laterally by the cylinder. So how do we find z? So z, we want to find, imagine a line through our region and increasing z and find what surface it enters and what surface it exits. So where does it enter? Well, if we draw, imagine that this is x, y, z again. If we're drawing a line in the increasing z direction, so my purple line right now, we enter at this flat surface, which is z equals 0. We exit at the paraboloid because it's bounded above by the paraboloid. What was the paraboloid? That was z equals x squared plus y squared. If we want to rewrite it in cylindrical coordinates, what is x squared plus y squared? So x squared So rectangular to cylindrical, x squared plus y squared is r squared. So let's write z equals r squared. R squared. So that's the z bound, 0 to r squared. Then we want to collapse the z-axis as we normally do. When we collapse it, we're left with this bottom part of the cylinder, this circle part, which I've drawn here. That's the shadow. Now at this point, we need the radius bounds and the theta bounds. So radius, we draw a line increasing radially outward. So this green line. R enters at 0 and it exits at 1. This is our circle. Our circle is x squared plus y squared equals 1, or r squared equals 1, or r equals 1. Then out of all the possible rays that we could draw, well, this is like a whole revolution. So theta is from 0 to 2 pi, or 0 to, wait, it's not 0 to 2 pi, it is 0 to pi. So r, wait, sorry, r doesn't go from, r goes from 0 to not 1, sorry. We have to rewrite our equation in polar. So what was our cylindrical equation? Our cylinder was x squared plus y minus 1 squared equals 1. If we rewrite that in polar, we end up simplifying to get r equals 2 sine theta. So that gives us our upper bound for r. Then theta, so theta, how do we find theta? Well, theta goes from, let me see, theta, if we're going, if we have the cylinder, okay, let me think. So we have this circle and we're drawing increasing lines. We want to find the smallest line. So that's going to be theta equals 0. And the largest line is theta equals pi. Because our region is this like, the probably like kind of split our region in half when we did the shadow. So theta goes from 0 to pi. And therefore we can rewrite our triple integral in Cartesian coordinates into a triple integral in cylindrical coordinates. Yes.
It comes to the circle in pi.
Okay, so r goes, let me see. So r equals, oh, because so everything in our cylinder is in the positive axis. So like it's kind of split in half by this positive octant or positive quadrant. So it won't go into the negative part. That's why theta is from 0 to 2 pi, 0 to pi. Okay. Any other questions on that problem before I do spherical coordinates? Okay, let's do spherical coordinates. So here's more formulas for your to memorize. So spherical to rectangular or rectangular to spherical. This may not show up, but there's also conversions for spherical to cylindrical and cylindrical to spherical. Okay, let's do a quick example. So it says, find a spherical coordinate equation for this cone. So we have this cone and we want to rewrite it using spherical coordinates. So does anyone have a suggestion for how I should do the first step? If we're converting this to spherical instead. And this is in Cartesian right now.
Square. Can you just do like the row cosine theta and then like solve it out?
Yes. So what was, let's look at originally. We had x is rho sine cosine, y is this, and z is this. So if we take what z is, which is rho cosine phi, and plug it in. So rho cosine phi equals square root. What was x? X was rho sine phi cosine theta. Rho sine phi cosine theta. And then we have that x is squared plus y was rho sine phi sine theta squared. And then we can simplify this. So this is rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. The cosine squared plus sine squared, that would end up simplifying to 1. So we're just left with rho squared sine squared phi or rho sine phi. So right now we have rho cosine phi equals rho sine phi. If we divide both sides by phi, so we're left with 1, and let's divide both sides by cosine phi. So now we have 1 equals tangent phi. When does tangent of an angle equals 1? Well, that's when the angle is pi over 4. So if we were to rewrite this equation in rectangular coordinates to its spherical coordinate, we get that phi equals pi over 4 describes this cone. Yes.
X squared plus y squared equals r, and converting this like this cylindrical coordinate to polar. Like
Yes.
something like you have there.
Yes. So the cone, the cone in cylindrical coordinates would be z equals r, or r equals some number, right? Yeah. So there's 3 ways to write the equation of a cone: rectangular, cylindrical, or spherical. And you could also, if you wanted to like use these formulas, you could have converted this to cylindrical first and then did cylindrical to rectangular. Either way works. Okay, any questions?
Yeah, I'm so sorry. Is it just how
Yes, the answer is phi equals pi over 4. That's the equation of a cone in spherical coordinates.
oh
So if you ever see like your region is bounded below by phi equals pi over 4, you know that it's going to be bounded by some cone. This is a cone. Okay, so let's do a triple integral question. So now we have Fubini's theorem for triple integrals in spherical coordinates. Okay, let's think about this question. So I say find the limits of integration over d in spherical coordinates, where d is bounded below by the cone. So we know this is a cone now, and above by the sphere. Okay, let me give an overview first. So how we're going to do this is we first want to find the row bounds. So you want to find which surface you enter, which surface you exit. Next, we want to find the phi bounds. Phi meaning like out of all the rays that you could draw radially outward, which one gives the smallest angle with respect to the positive z-axis, and which one gives the largest angle with respect to the positive z-axis. Then to find theta, you can collapse the z direction and find your theta. Like, is it a whole revolution, or what's your theta? Okay, so let me give you guys a minute to think about this question. Maybe like draw it out first. And at least find what the row bounds you think are. Okay, so let's see. Okay, first, well, they already tell us what shape it is, so why don't let's just draw it. So we're bounded below by some cone. So I'm just gonna draw some cone here. And we're bounded above by a sphere with radius 1. So let's just draw a sphere here. Approximately sphere. Then we first want to find the z bound. So z bound is, we want to imagine cutting a line through our shape radially outward. So if you were to start here and we draw a line radially outward, well, imagine this is like the origin. You start at rho equals 0 and you exit at this. What is this equation? This curve is our sphere, which they told us is rho equals 1. So our bounds for rho are 0 to 1.
How do you know you're starting at the bottom of the curve?
Because our shape is this shape here. So like this part doesn't exist. We're starting here. Like any line you draw radially outward, you can draw a line this way, you can draw a line this way, you can draw a line this way. They all start at the origin and you're going outward. So increasing outward, you always hit the sphere last.
I didn't know that the sphere like goes all the way to the bottom. Like why can't it just like cut through the middle of the cone?
Oh, like the sphere goes like this?
Yeah.
Okay, I guess maybe you could have, I should have drawn the picture as like this was the origin. Because if you think about a sphere with radius 1 centered at the origin, and you think of a cone always starts at the origin and goes upwards.
Yeah.
Is that, so like,
But how do you know that's something at the origin?
so you could, if you don't, so if you're, so remember that when we converted this, so like how would you draw this? That's a cone with its point at the origin going upwards. And we saw that that was phi equals pi over 4. So now we just changed the phi number. Our phi is pi over 3. So if you're ever unsure, you could always convert back to rectangular coordinates to see, but yeah. Okay, so back to this. Okay, so now for the phi bounds. So we know that our rho goes from 0 to 1. What about phi? So phi is, you want to draw lines. So let me, okay. Let me redraw our thing. So we have some sphere with a cone. So if phi goes from, so you always start at the, like this axis. And this is our positive z-axis. So we want to draw a line parallel to the z-axis. The angle that this makes with the z-axis is 0. It's just straight. The angle that this makes with the z-axis, well, if the z-axis is vertical, and we have this angle here, that would be phi equals pi over 2. So the angle that your ray makes with the z-axis is your phi. If we had some line here, that's phi equals negative pi. Because this angle, if you had a positive z-axis and we have this angle here, that's 180 degrees. So we want to see, out of all these possible lines that we could draw outwards, what is the smallest phi? Well, the smallest phi, no matter what, it's going to be parallel to our z-axis right now. So phi equals 0 is our lower bound. Then remember that our region is just this cone part. This part. So any other ray we could draw a line here, but the largest line we could draw is this specific line, the line that marks our cone. What curve is that? Well, that's the curve equation of our cone. And what did they say our cone was? They said our cone was v equals, let's see, v equals pi over 3. So this line right here, the angle that it makes with respect to the positive z-axis is pi over 3. So our phi bounds go from 0 to pi over 3. Pi over 3.
That would be also pi, right? That would be minus 1.
Positive pi. Okay, then we can imagine collapsing the z-axis. We know what it should look like. We kind of get like a shadow that looks like a circle. Well, it's okay. This question is different from the last question, but this question, we have a full revolution. So the angle is 0 to 2 pi. And you can also imagine that because imagine your sphere is now hitting all quadrants, like negative and positive. So you have a whole revolution.
We know it's 2 pi.
Because you can imagine our sphere, this sphere actually, if we have this cone that's like part of the sphere, so remember we're bounded above by the sphere. So when you collapse the z-axis, you get like this shadow. So it's in the positive quadrant and the negative quadrant. So it has to be 0 to 2 pi. Any questions on this problem? Okay, let's move on to substitutions. Okay, so this is going to give us the reason for why. So at the beginning, I said that A equals R equals R drg theta. So we're going to get some intuition on why that is. So substitutions. We're always going to want to compute the determinant of something, or the determinant, the Jacobian matrix. The determinant of the Jacobian matrix. So for example, in polar coordinates, if you're converting from r theta, polar, to rectangular xy, we know that xy is given by r cosine theta, r sine theta. So right now we have inputs, 2 outputs. If we wanted to compute the Jacobian of our output xy with respect to our inputs r theta, well, we know how to compute the Jacobian. That's you look at the first output in the first row with respect to the first input and the second input, and so on. So if you actually computed this, what is the derivative of x with respect to r? The derivative of the yellow thing is cosine theta. What about the derivative of this with respect to r? Well, that's sine theta. Derivative of x with respect to theta, that's negative r sine theta. Derivative of this with respect to theta is r cosine theta. And when you compute the determinant, you end up getting r. Okay, and you could do this. I didn't do it for 3x3 matrix, but this is the general one we use for polar coordinates. And in cylindrical coordinates, if you computed the determinant of the Jacobian matrix, you'll also see that you get r as well. Because remember when we were doing the v, we also added another r here. And spherical. So in spherical coordinates, why do we end up, oh, I don't think I gave this definition yet, but this will be important. We get rho squared sine theta. So you can think about in spherical coordinates now, we are going to have the same thing, where we have to add this extra component. Okay, so what does our formula say? Our formula says that the integral of some function of with respect to x's and y. So let me write it here so we can reference it. So integral of f with x1 dx1 dxn equals integral of f with respect to x of u1 and dot x u1 u n I'm writing this because it'll be important when we use it. This Jacobian matrix. EU1. Okay. So that's our like outline, our template that we're going to use. So now, how do we get for the, when we're doing polar coordinates, right? If we wanted to convert from X, Y, so we said that, what did we say for polar coordinates? So we said that in general, for polar coordinates, we're gonna have integral of some function where expression has x's and y's, dx dy, or dA, is gonna end up being some integral, but we rewrite our expression so that it just has r's and thetas, right? So it's some function in terms of r's and thetas. And then when we converted this dA part, what is dA? That's r dr d theta. R dr d theta. So how did we use this theorem to get this result, which we always use when converting integrals? Well, so right now our x1s and x2s are x and y. Our x of some input, this is just meaning like your other like output, which in this case is r and theta. So when we have f of x, y, you see it's connecting x, y equals integral of f of what is our output of x, y if we're going from x, y to r theta. Well, f of r theta, what is the Jacobian of this, the determinant of the Jacobian? Well, we just calculated that the determinant of our Jacobian was r, right here in purple. That's how this is r. And we just have d of our output, so r and theta. R and theta. Okay. Any questions on how I got that? Okay, and you can do the same thing for spherical coordinates. So in spherical coordinates, it ends up being that some function in terms of x, y, and z is going to be the other function or the same function, but rewritten with different terms or parameters. So rho, phi, and theta. And we're going to have this rho squared sine theta part. So that's our determinant of the Jacobian. And d theta, d phi, d theta. D rho, d phi, d theta.
So the Jacobian is
The
that, right?
Yes.
I mean,
Yes. So this is highlighted in yellow. That is the determinant of this partial with x, y, z with respect to phi, rho, phi, theta, if you calculated it. Just
but
like,
that's super long, right?
yeah, so which is why you don't really need to like derive this usually. We just memorize that whenever we're doing spherical transformations, just add this extra rho squared sine theta. Just like how if we're ever doing polar transformation, we just memorize that we need this extra r here. We don't actually like sit through and compute it. But they could ask you to compute like something more simpler, like rectangular to polar.
But this is rectangular to spherical, right?
Yeah.
You would use that. And from spherical to, so from cylindrical to spherical, which one would you use?
Then we don't typically go the other way around, I think. I mean, you do know there is a property that if you wanted to switch it, you would do the inverse of this. So maybe you could, but I don't think I've seen an example of it yet. Yeah, but if anyone sees an example of it yet, let me know. Okay, any questions on all this like substitutions. Okay, let me go over this example real quick as well. So this example is very tricky, I think. So we wanted to evaluate. So now we've gone through how do you do substitutions? How do you actually evaluate it? Like, what do you want to choose for different substitutions? Well, what you want to choose is sometimes a bit tricky to decide. There's no like set way on doing it. But if you wanted to do substitution, evaluate it. Here, this is your function. Your region is described by y between 0 and 4 and x between this. So you might ask, if x is between y over 2 and y over 2 plus 1, how did our region end up to be this triangle? Like, it doesn't make sense. Well, that's because we always try to simplify things. So like our y bounds are between two numbers. Our x bounds, we want to also make it between two numbers. Or like we want something here so that we have other bounds with two numbers. So if we simplify this in green, which is what I'm doing here, I multiplied everything by 2 to get our second line. I subtracted y from both sides to get this line. And I divided by 2 to get this line. So we have this expression with bounds from 0 to 1. If we rewrote that expression, so 2x minus y over 2 equals 0, that's our lower bound. Well, that gives us y equals 0. So that is this line, y equals 0. Then if we rewrote it with our upper bound, which is 1, you end up getting 2x minus y equals 2, or y equals 2x minus 2, which is 2x minus y over 2 equals 1 times 2x minus 2. Oh, this line you get y equals 2x, which is this line here. And the second line, you get, wait, why did y equals 2x times 2. Okay, maybe this did not work as I planned. 2x minus y. Okay, let's continue with the, yeah.
Can you explain again where you got the original balance? Like y goes from 0 to 4.
Oh, this they gave us as a question.
Oh,
Yep. So if they gave us this question above right here, and we wanted to evaluate the double integral of our function over this region, how do you do it? Using substitution. So first, so the idea of substitution is that we want to choose a u and a v so that our integral ends up being simpler. So if we rewrote this green, so without drawing, let me rewrite this green as these bounds. So we don't want this like complicated 2x minus y over 2. So let me use that as our u. So I call u equals this expression. Is there anything else complicated I see? The only other complicated thing I see is this y over 2. So I choose v equals y over 2. Then, oh, so now here's where you might need to compute the Jacobian. So if we compute the Jacobian going from this xy to our uv, then we calculate the Jacobian, find the determinant, we get 2. So what does this formula tell us about how we could rewrite our integral in terms of u's and v's? So right now we have things in terms of x and y. So right now we have double integral of xy dx dy. But we want to write it as an integral of du dv. Integral of f of uv du dv. So we need to find what is that Jacobian? Well, the Jacobian we found is 2. I'm going to have a 2. So this means that if we want to substitute variables so that we're doing things in terms of u's and b's, we're gonna need to multiply it by an extra 2. Rewrite our expression in terms of u and b. So this equals this by our formula, our original formula. So continuing, we got that Jacobian matrix. Now we also need, what are these like new bounds? Right, so let's rewrite our bounds. The original bounds were y equals 0 to 4, and this was the original bounds. But now we said that we set v equals y over 2. So y equals 2b. So I put in 2b for y, and now I solve for v. So now the bounds for v are 0 to 2. Then what about this thing? So we simplified to this point. So this was still our original. In yellow, it's still our original bounds. We set this whole thing in here to u. So now it's just the whole thing is u from 0 to 1. So our new bounds are in green. So see how we simplified from this complicated yellow thing to a more simple green thing between 2 constants. And so when we plug it into our formula, we have, as I said, this double integral with our bounds plugged in, our new bounds. We have a 2 from the Jacobian. And then our expression, our original expression was 2x minus y over 2. We said that's u. So we rewrote our expression in terms of u. So that's u, and then du dt. Okay. So that's how I went from this integral in terms of x's and y to an integral in terms of u's and v's. Any questions on this problem? Yes.
Does it usually work out so that like when you solve?
Yes, it should all, if you pick the correct u's and v's, it should all simplify nicely. So like it should be an easy, shouldn't be too complicated. Yeah. Yeah. Okay, and there's not I don't know, you kind of have to do multiple problems to kind of get the hang of what do you choose for u and v, but usually it's like what you see is complicated that you don't want is what you're trying to choose for u and v. Yeah. Okay, let's move. Any other questions on that? Yes. For v. Oh, like why didn't I make this v instead? 2x minus like I can make this maybe. Oh, for like how I do the region. Yeah. I don't think the drawing of the region might be that important. I'm not too sure how I got it again. But you see how we like solve the whole problem without even drawing the region. So yeah. Okay. Okay, final thing, let's do surface integrals real quickly. So surface integrals are even more complicated now. So we have some R, and surface integrals might require some parameterization. So here I just wrote out the formulas. If you have like a curve in a plane or a surface in a space, how do they look like in their explicit form or implicit form? Implicit form means you just have something equal to 0. Explicit means you have like some variable equals something. And in parametric form, everything should be in terms of your chosen like input value. Okay, so let me just do an example. Okay, if we wanted to compute the double integral of g, where g is that and s is our surface is that. So this is our question. How do we compute this surface integral? So step 1 is we want to parameterize it. So we want to parameterize. What does parameterizing mean? Well, right now we have an equation in terms of like 3 variables, x, y, and z. we don't want 3 variables. Instead, let's get rid of one of the variables. So right now, if we have x, y, and z, so imagine this is x, y, and z. If I set z equal to r, then now we can rewrite our like parameters as just something with r and theta. So now we just have 2 terms instead of 3 terms, x, y, and z. So I've eliminated one variable. Everything just has r's or thetas. That was our first step. So that was, yeah, parameterizing. Then step 2, we want to write this r sub I. So that's the derivative of our expression with respect to r. Maybe this should be r. So if I take the derivative of this with respect to r, I get cosine. Derivative of this is sine. Derivative of r is 1. Then this r sub theta, that's your derivative with respect to theta. So if I took the derivative of this, I get negative r sine theta, r cosine theta. There's no theta here, so 0. And I compute the cross product of these 2 things, and I get this expression. Then I take the length of it, and I get r square root 2. And so the idea is similar to our original theorem. We kind of need to find something, but now our something isn't necessarily a Jacobian matrix. It's what we get from doing the length of Ri cross r theta. So from this, we have r square root theta that acts as like our this part, and we have dr d theta, and this is our d sigma. So in previous examples, we found that dA is r dr d theta, dv is dv or you have the spherical one, which is rho squared sine phi, I believe. And now we have that this d theta, d sigma is I cross r of r and theta. So we're, yeah.
Is there a difference between the r sub r and the r sub I, or can we use those interchangeably? And so, like, what is that? Can you just go over with the r sub I?
Yes, r sub, oh, sorry, it should be r sub, just, you could say I or r. I is just so that you don't have like 2 r's, I guess. But r sub I is the derivative with respect to r. R sub theta is the derivative with respect to theta. Yep. So I think I have I so that you don't have like double r's. Okay, and now that is our d sigma. And so when we're doing our integral, so this was our original integral in yellow. We were trying to do the double integral of x squared d sigma. We want to convert using our surface integral. So x squared, change it to polar coordinates now. So x is r cosine theta squared. D sigma, which we just found, is square root 2 r dr d theta. And then you can compute this integral and get your answer. Okay, any questions on, yes. Cross, that's just the definition of d sigma. So the definition of d sigma is this like length of ri cross r theta, dr d theta. Just like how in previous ones, we found that what the Jacobian is. Instead, we're just finding what this is. Okay, then with that, recitation is over. So let me stop screen share.
So do you do the cross product